Okay, so let's now start the exercises. So in this first one, we are given two sets x and y. Both are subsets of the set of real numbers, of course. And x is a subset of y and y is a subset of the closure of x. Then we have to prove that the closure of y is equal to the closure of x. So let's see the solution. From this first containment, we are immediately going to get something. Since x is a subset of y, lemma 9, 1, 11 implies that x closure is a subset of y closure, and this is that lemma which gives us the elementary properties of closures. We have already proved this. Okay, so from there we are getting this containment. Now in order to get equality, we need the reverse containment as well. Similarly, this other containment is going to give us this. This implies that y closure is a subset of the closure of x. However, by exercise 6, this is equal to x closure itself. Hence, y actually turns out to be a subset of x closure. So now you combine these two containments and get equality. Now you may of course ask one question: is it really okay to use some result that is going to appear later on like this now itself? It's actually not a problem, because in the solution to this exercise we will not use this result. Had that been the case, we would have run into circularity, which is not allowed. I mean, if you have an argument that is going in circles, then actually you are not proving anything, but luckily that's not the case. Okay, so that is the solution. Now next, the second exercise and the third exercise ask us to prove the lemmas. For example, the second one asks us to prove this, but because we have already proved it in the course of going through the section, so 912 is already solved for us. Similarly, 913 asks us to prove lemma 9113. That also we have proved already. So this is also done. So let us now see the fourth one. Here give an example of two subsets x and y of the real line such that the closure of x intersection y is not equal to the intersection of x closure and y closure. You remember that while proving lemma 9-1-11, we have proved that this set is actually a subset of this intersection. And there itself, I think this question also arose whether we can always have equality. Now, I cannot remember exactly if we address the question there itself. But anyway, this exercise asks us to show that no, we cannot have equality in general. So we now have to come up with two such subsets that give us inequality. If we have already answered it there, fine, let's just do it once more then. Otherwise we need this. Consider x to be this open interval and y to be this other open interval. Okay. Now we have already proved in one of the results, I think it is lemma 9-1-13, where we proved that the closures of all of the four types of bounded intervals, that is any open interval or half open interval or the closed interval, the closures of all of them equals the closed interval. So from there we get this. Then x closure is the closed interval and y closure is this closed interval. So their intersection is the intersection of these two, which is this singleton set 2. But what about this though? Note that although x bar and y bar are not disjoint, but x and y are disjoint, there is no common point. That single common point 2 that we have here, that is not available here because 2 is not an element of either of these sets. So in this case the intersection is empty, but we already know that the empty set has the closure which is also equal to the empty set. So that's how you have inequality. In any case, this is a subset of this that we already have proved, but equality is not necessarily true. Next, 9-1-5 then asks us to prove lemma 9-1-14, which also we have already done. And so let us now see exercise 6. In fact, this is the one we used in the solution to the first exercise. Let x be a subset of R. Yeah, instead of writing that much, let me just write in short like this. Let x be a subset of R. Then the closure of x is a closed set. The closure itself is also a subset of R. So as a subset of R, it's a closed set, which means that its own closure is equal to itself. In fact, this is the identity that we have used in that first solution. Moreover, if y is a closed set containing x, that is this, the closure of x is also contained in y. In other words, I am not writing that here, okay. All of these things ultimately mean what? Let us just see that for once. So this exercise has two parts, right? First we have to prove that X closure is a closed set, okay. And in the second part we have to prove that if Y is a closed set that contains X, then Y also has to contain X closure. Now combine all these things with the fact that X closure also contains X, and then that just simply means that X closure is the smallest closed set containing X, because X closure is closed, that you prove here, and it contains X that we already know. But if you have another such set Y which is closed and it contains X, then it has to contain X closure. So in that sense, X closure is the smallest closed set containing X. Now let us prove this. So first we need to prove this identity, and that means that those two reverse containments, that is they are inverses of each other. So one of them we already know. We know this thing, that X closure is contained in this double closure. Now the reverse one. So let X be any element in this set. That means what? It means X is an adherent point of X closure, because it belongs to its closure. So that's why for any epsilon greater than 0, there exists an element Y in X closure such that Y is epsilon close to X. But we won't take epsilon itself, but rather epsilon over 2, which is say a new value of epsilon, such that Y is epsilon over 2 close to X. But at the same time, this is not where the story ends, because Y is also in the closure of X. So Y is an adherent point of X. So there now exists a point Z in X such that Z is also epsilon over 2 close to X. Well, oh sorry, it's not X, it's Y, because we are getting Z for Y. Then what do we get? The distance between X and Z by triangle inequality for distances is less than or equal to the sum of these two distances. So that's it. What have we shown? We have shown that for any point X and any epsilon, well, X was first chosen, then for any epsilon positive, there exists an element Z in X that is epsilon close to X. So that makes X what? It makes X an ordinary adherent point of the set capital X, or in other words, it makes X an element of the closure of X. We thus have what? X was an arbitrarily chosen element of this set, and we have shown that it then belongs to this set. So the closure of X is contained in the closure of X. Now you combine this containment and its reverse containment, and that gives you the equality. Now we prove the second part. Next, let Y be closed and let Y contain X. Then by elementary properties of closures, the closure of X is contained in the closure of Y. But because it's given that Y is closed, by definition the closure of Y is equal to Y. So that's how X closure becomes a subset of Y. So that completes the solution. Next, 7. Let n be a positive integer and let x1, x2, etc. up to xn these be closed subsets of the set of real numbers. Show that their union is closed. In other words, the union of finitely many closed subsets of R is again a closed subset of R. Or in other words, if you consider the collection of all closed subsets of R, then that collection is itself closed in the sense, in the algebra sense of closed, okay, is closed under the formation of finite unions. Its proof is very easy. Do you remember this property of that involves closure as well as union that we proved in lemma 9111, that when we have union, then closure distributes itself over the union. Here we have equality, but there in that one, when we have intersection, then equality is not guaranteed. We have containment, however. Now one can use induction and this fact to extend this to any union of finitely many sets. Okay. And here we are not talking about just closed sets but any subset of R. What I am trying to say here is that if you have in place of two sets any n number of sets where n is a natural number, then the similar thing happens. Okay, so I'm just simply going to write this. Using that fact, that extension of this result, this closure by that extension is equal to this union. But keep in mind that before writing any such thing, ideally speaking, you have to supply a proof. But for your own sake, whether you want to save some time or you have some other reason, you can write like this, but be prepared to supply a proof when someone asks you for details. Okay, if you have that, then you can do some such things. But now it's also additionally given that all of these sets are closed. So that's why each such closure is equal to the set itself. That means the closure of this union turns out to be the union itself, and that's why the union by definition of closedness is closed. So it's less of a solution and more of a hint. Okay, but it just tells us everything that we need to solve this. And let us now see one more. When it comes to closed sets, they behave well under the formation of finite unions. That means if finitely many closed sets are there, then you can unite them and again you have a closed set. However, when you bring intersection instead of union into this situation, then finiteness is not needed. Any intersection where any number of closed sets are involved is again going to give you a closed set. So this next one is about that. Let I be any set, and in order to emphasize that fact, the author has written possibly infinite. I may be infinite, I may be finite, we don't know. I is just any set. And for each element alpha in I, let X alpha be a closed subset of R. In other words, we are now looking at an indexed family of closed sets where the index set is I. Its elements are labeling the elements of the family. Then show that the intersection of all the elements in that family, that is all the closed sets, is itself a closed set. These results, we will see later, are parts of a much more general situation when we study topology. There is another class of sets which are more commonly used in topology. They are open sets. Okay, because it is somewhat cumbersome to keep writing this notation, so let's give it some name. Let us call it X. Okay. Now, what is it that we have to prove? We have to prove that X closure is equal to X. That's what implies closeness, since X is a subset of X alpha. Why? Because X is their intersection, so X is in fact contained in each X alpha as a subset. For each alpha in I and each X alpha is closed. That is already given. We have X closure also contained in X alpha, and this is coming from that sixth exercise, right, where you think of X alpha as Y and X as X. So Y is closed, that is given, then Y would contain the closure of X as well. For each alpha in I. This implies, so now just like the set X, the closure of X is also a subset of all the X alphas. So automatically the closure would be a subset of their intersection as well, but that intersection is nothing but X. So that's why we have this. But that implies what? Since we have the reverse inclusion already, so this further implies equality, and that itself implies by definition that X is closed, which is what we wanted to show, because this is X. Right, so that completes the solution, and let me just end the video here itself. There are other exercises also that we will solve next Sunday. And this coming Tuesday we have another upload, but because we are going through exercises of group theory from Herstein I am talking about, so in place of a video you will get a community post. So there I will solve some problems, further exercises. We already have solved, I think right now we are in that section named another counting principle, where in the previous post I solved exercises 4, 5 and 6 I think. So the other ones that come after that, they will appear, okay, along with their solutions. So see you on Tuesday with that. Until then, this is me, Lucifer from A Mathematical Group. Have a nice night.